Cosine, the guys who brought us Hyperscout 1, who'll be talking about, what will you be talking about, Marco?
Thank you.
Okay, you introduce yourself, all right?
So, thank you. Marco Esposito from Cosine Management System, Dutch company. I'm going to talk about Match, an activity that just started with actually Esrin here. Match stands for Machine Learning Tool for Calibration of Hyperspectral Data. So the presentation is structured such to give you information about the hardware that we have produced that is actually collecting the data for making this match let's say, developed. And therefore, I will be talking about Hyperscout 1 and Hyperscout 2, that are two payloads that one in flight already and one is going to be launched soon to give you a better understanding of what we are trying to do. And then, yeah, mostly I highlight the plan that we have for this match tool, and now we are indeed in the collecting phase. So I will be discussing also a bit of the operations we are doing. So Hyperscout is as far as we know, the first full-fledged hyperspectral system of this class of 1.3 kilograms that is currently flying with a 6U platform in orbit since February 2018, has been developed with under ESA contracts, GSTP contracts, and the assets of these systems lies in a large field of view in both directions, talking about 31 degrees by 16 degrees. So from the orbit we are talking about 300 kilometers by 150 kilometers, more or less. And also, let's say, the development went a lot into make this telescope alignable in a very short time. Actually, we align it during production. Therefore, we can enable production of large numbers, and that's very useful for constellations, of course. And the other big asset is the processing chain that we developed with our partners in order to do directly in orbit the processing from level 0, so from raw data, up to what we call level 2B, that is geophysical parameter of the actual application. And that has been, let's say, developed in the last few years, again, during GSP contracts. And we are now in the phase of exploiting the system that is in orbit and try to do experiments and see how far we can go. The application that have been developed are the one listed here. So it's a set of applications that range from indices, so let's say relatively simple in terms of computation, to more complicated one, like change detection for land cover land use, that requires a bit more of power, computing power. So it's a bit of a balance and in order to, for us, give a bit of freedom to see how far we can go in orbit directly. So we are, as I said, at the moment in this phase of exploring this kind of activities. And but the bottleneck is, of course, the downlink capacity. So we are doing this to enable hyperspectral from nanosatellites. Hyperscout produces in the order of a gigabyte per watt. So it means if there is a decent duty cycle, we are talking about terabytes very quickly in a few orbits. And therefore, as you can imagine, it's practically impossible to download this data. So this approach is useful to first have your decision on what to download in an educated way. So you can download first the information with the calculation done in orbit, and then based on this information, you can decide what can be downloaded, what not. Or you can use the information directly for early warning. So for fire hazard, for flooding, change detection, you can get down directly information. You work with that. So if there is a threshold that has been exceeded, then the user can use this information to act on ground, so, or I don't know, to investigate better with high resolution satellites, go with UAVs or go in situ. That's a bit the idea. And this, in the end, if you consider one Hyperscout that is acquiring and in parallel running processing tasks, you can imagine a scenario like this, where you have an orbit where there are different sites that you want to acquire, sites applicable for different applications, again, the ones that we have been developing. And this is a real case that we want to do in the future. So during an orbit, we can pass over all these locations, so Mozambique, Tanzania, Uganda, and so on, where we have actually partners running experiments on ground. So the idea is to really acquire and process and provide information and see whether they are meaningful compared to ground systems. This is to give you a bit the framework. So the system, as I said, has been launched in February. In March, there was the first commissioning, and now we are right now actually in the middle of the acquisition for calibration and for the application, validation of the applications. So what you see here is a few hyperspectral frames. So the system is a push broom. You need to actually to acquire a large number of frames before you can build your level, your data cube. And this is one of these frames. And so a long track is actually varying spectrally, while across track you get the same wavelength. So each line is a different wavelength. So you see in top left, one of the first frames we got over Cuba. On the right, a very nice one over California, where we got, I will say, a multispectral set, so a number of frames that allows to build a multispectral system. And then on the bottom left is one over calibration sites. This is over Algeria, so this is typical invariant size used for calibration, and that's where we are focusing now to get the performance of our system known to us as well. And let's say top right, you see a bit the plan we have, so which kind of regions to acquire, and mostly have been acquired, so we'll keep going until the end of the year. The interesting evolution is that we are already working on a second generation called Hyperscout 2, and we are actually very close to deliver the flight hardware. And this is in a context of a mission called FSSCAT, for which the applications are high resolution solid moisture and ice extent and ice thickness. Hyperscout is used in this case with the spectral bands to improve with the pixel deconvolution, the resolution taken from radiometers and from reflectometers. So the partners you see on top, and the main scientist, principal scientist is in UPC, the University of Catalonia. So the interesting features on top of what are already present in Hyperscout 1 is that beside the veneer hyperspectral part, we have also 4 thermal bands, so it starts to be very interesting because the application base becomes wider. And in this configuration with this satellite, we can exploit the full field of view, so we get really the 300 kilometers, while in the Hyperscout 1 we have some mechanical limitations, so we get to about 200. And we also make sure that we can talk to different platforms, so be a bit more standardized in terms of interface, software interfaces. And the important point is that doing this project with Esrin, so we get also a chance to validate some data products with Copernicus user base, so some of you for sure. This is very, let's say, a short timeline, so we have to deliver it in January and for flight. But we are considering, actually, there's been a news item this morning from the Aspaker, the director of Earth Observation, that ESA is working on flying an hardware artificial intelligence accelerator, so the Myriad 2 Intel chip, system on chip. And actually this is us discussing whether this will be the case, and we are working on now studying whether quickly we can integrate this board and flying in space. So this will open again another let's say, route for doing experiments in flight. We already have a CPU, a GPU that we can use for different experiments. On top of it, now we can run also the Myriad 2, so with system on chip. So we can see really differences. We can run application, and actually this will be open also to partners to collaborate with us and try out new ways of doing Earth observation. What you see on the top bottom right, you see the 2 systems, so how they are changing, and there will be both in flight, so we can have also, let's say, interesting application where the intelligence is distributed. So now our 2, we plan to launch more, so this can become a very interesting flying laboratory and try to play with the interesting asset in space. So MEDGE, finally, is a project indeed started following these evolutions, and to explore indeed how machine learning can help improving our data product. And so being Hyperscout 1 and 2 will be one of the first hyperspectral system producing data from space. So this is really a nice test case for seeing how much we can use these new techniques, or not really new, but let's say applying these techniques to cross-calibrating Hyperscout with Sentinel-2, also with Landsat 8, but in general with institutional satellites. This is why, because Hyperscout is 1 kilo. So you understood that it's extremely small, so there are no calibration equipment on board. So we rely solely on vicarious calibration techniques. And while Sentinel, we know very well, is a properly done system, big, full of calibration devices, so we assume is very stable, very accurate. So we want to exploit that. And we want to cross-calibrate and make our product, but in general, product of constellation, somehow aligned, so have a spectral response function that is actually calibrated to each other. And therefore, we can exploit the small satellites, usual revisit time, because you want to have many space, with, in this case, a lot of spectral bands, talking of 45 plus some in the thermal, and exploiting the resolution instead of the multispectral Sentinel. And therefore, in the end, you want to have a blended product that has the 10 meters of Sentinel, the 45 bands of Hyperscout, and the revisit time of a constellation of Hyperscouts that can be. We are planning some. You will know in the future, but will be extremely high revisit time. So this is the first step in this project. We are just started. We are trying to now to see how much we can do, and now we are in the middle, as I said, to have acquisitions that are usable also for this project. I think I will not say too much on this slide, but this is to show a little bit the different systems of Sentinel, Landsat, spectral channels, and also Hyperscout that you see here on top left. So this is the hyperspectral part in the visibility and infrared, and the thermal part. So that goes from 8 to 14 broadband, but we have 3 bands between 8 and 12.5. And so this can be compared definitely with Sentinel-2, A and B, with Landsat 8. And when also Hyperscout 2 will be in orbit, we can start playing also with other Aster modules and so on. Here there is a bit more detailed table that you will know. The remarkable details are the spatial resolution of Hyperscout, that is 70 meters. So for some can appear coarse, but for the number of bands and spectral resolution, it's actually extremely good, and also for the size of the system. And while we compare with some bands of Sentinel that varies from 10 to 60 meters, so you will know very well. And but the matches, they match very well because the spectral range is the same. So it will be a very interesting exercise. So this is the approach we have. Now we are, let's say, in this phase where we are detailing our CalBal plan, but we have also to acquire data for our in-orbit demonstration. So we are trying a bit to make sure we have reasonable simultaneous data with Sentinel as well. That anyway was set from the start. And on top of it, we also plan to fly a night-bomb version of the hyperspectral system so that we can also do, let's say, properly understand our system, calibrate with conventional ways first, understand what are the pro and cons of our system, and most likely the idea is to then get a training set from all this data and compare 1 or 2 bands from the hyperspectral with the multispectral of Sentinel. So that will be the first step. Really very small steps. We want to be careful and not to shoot too high, but this is what is happening. And on top of it, we are this project is together with ITC of the University of Twente, and they are running a tower in Speldebos, that is a forest in North Holland. There we will have the actual ground truth. There will be a spectrometer, a field spec that will be acquiring a very high resolution, spectral resolution. So for that ground point, we want to then extend the calibration of our airborne strip, and then on top of it, we can play then with satellite data. And let's say ultimately we want to, as I said, play with Sentinel, Landsat 8, and Hyperscout. So that's let's say the idea is to. There are ideas, first of all, that's nice. One is to act on the level, what you call 2A, so on the real application following L2A, is the data cube georeference calibrator, so to act really on the radiometric calibration. So to look at our spectral data and the reference data, that in this case will be Sentinel, and do spatial and spectral matching before we can start comparing this data. And then we can also look how our system is stable, so actually compare time to time, also based on the seasonal variation of the scene. So to play with all these parameters and come up with indeed machine learning tool that can help in making this better. Or, that's still under discussion, where to look directly at the application level. So in the case, this is from a famous paper comparing MODIS NDVI and AVHRR NDVI that were very different, they were biased. So this could be also another approach to calculate parameters, geophysical parameters like NDVI or others, and try to compare them and see with machine learning whether we can remove this bias. We are now exploring what tools to be used. I think there will be also more discussion with the agency here. Perhaps we'll involve some more experts to see which one are the best. We are still exploring again, and these are the typical usual suspects, let's say. And these are the sites. This is interesting for you to know that we are gonna not all, let's say, but this is our set available to us. So first of all, instrumented sites from the RadicalNet, let's say, network, and pseudo-invariant calibration sites, like the typical, again, Libya, Algeria, and so on. And more interesting for application will be the land sites that we are acquiring for the IoT anyway, so will be used also for this project, plus water bodies, like one interesting one is in US, Lake Erie. And as I said, so the airborne part will be crucial to understand our system. These are a few data acquired this week, actually. So what you see on the left, it's Hyperscout frame at 70 meters. What you see on the right, Sentinel-2A, the B4 band, that I think is about 600 and something nanometers at 10 meters GSD. So you see, of course, the 1070 is a difference. But so these are almost, let's say, a few days difference. So one is 5th of November, one is 7th of November. So it will be used as well. This is over Libya 4. So you see, again, GSD 70 meters from Hyperscout. Hyperspectral frame, you see also here the oxygen lines that absorb very nicely. And the Sentinel-2B satellites. I have here a video just to let you understand what means acquiring hyperspectral data with our system. Yeah, no, it's short, it's 20 seconds. And this is an acquisition that also happened this week and shows you, this is a real time. So this is the actual time lapse in space to acquire the full data set from Hyperscout to then produce DataCube. You can see here, now there is no time, but I can show you offline, so how actually few fields pass through the red edge. You can see different response of the system based on the wavelength. So this again is, let's say, 9 Sentinel-2 tiles over California to actually have all the ingredients for cross-calibrated with Hyperscout. So what you see here is a hyperspectral frame from Hyperscout. This is the airborne acquisition. As I said, we have this tower in Spelderbos, and we will be doing this, hopefully, if we get enough budget to do this every 2 weeks from now to the summer of next year. So we have really a very nice data set. And it is in discussion also with China, the Tibetan Plateau. We have also an airplane there with a customer that can be used for the same thing. That's it. Thank you.
All right, thank you very much. Questions for Marco, for cosine? Nothing. In that case, I have one question. Why is, okay, onboard processing is happening a bit all over the place. Brain and space, I know we're responsible for the nickname. Why is it important to put artificial intelligence on board? Why is that important, especially for you as a mission operator?
Yeah, for me, from our point of view, is indeed for enabling the use of hyperspectral systems. The real bottleneck is data. Also for Sentinel-10, the hyperspectral big mission that ESA is planning, I think will be the same. So it will be a bottleneck. You cannot download all the data. So you need to be intelligent in doing data infading, understand what is actually needed to be downloaded. You cannot download old data blindly. That's my main thing. And that's one, and second is the actual operation you can do. So in real time, you can drive operations doing, of course, hazards and flooding. This is the typical, let's say, hazard management. But very importantly, you can enable hyperspectral from space, finally, from constellations. And they have another insight on phenomena. So the other component is spectral variability, not only the spatial one.
Okay, all right. Thank you very much. We would like to introduce then Sasso, who will be talking about data science for space.